Hello. Today we'll discuss about resolving power of an optical instrument. The resolving power of an optical instrument is the ability to distinguish between two closely placed objects. So when you have two objects placed side by side and you want to see through this some optical instrument, then if you are able to see it distinctly, properly, then we will say the condition is the resolved. And the power of this resolution is known as resolving power. Here we will discuss about three optical instruments, the main three optical instruments. The first one is microscope, second is the telescope, and the third one is the grating. So in microscope we used to use to see a closely placed object. So small objects we used to distinguish by using microscope. So the definition refers as the resolving power of a microscope refers to the ability to distinguish between two closely spaced objects as separated. Here you have object, they are very close to each other. Now you can see through this eyepiece. So when they are distinctly visible, they are known as the perfect resolution, and the power is known as resolving power. So you need to follow this mathematical relation to have a higher resolution. So here D is given as 1.22 lambda divided by 2 mu sin theta. D is the distance between the object place and this lenses. This distance is represented by D. Lambda is the light used. Mu is the refractive index of this medium, actually lens and that medium. This is represented by mu. Theta is that angle. So this is forming a cone. So the half angle of this cone is represented by theta. And this cone sometimes is represented by numerical aperture. So how much light you will be able to gather, it is represented by numerical aperture. So if you are able to satisfy this condition, the microscopic particle will be properly resolved by the microscope. So what are the criteria? Obviously if D is small, better resolution, it's very close, there will be better resolution. Now if you are using shorter wavelength and a higher numerical aperture, obviously you will be able to dissolve the system. But the problem is if you are very close to each other, then there will be a possibility of diffraction. So you really cannot cross this diffraction limit. If you are crossing the diffraction limit, then the problem will be more complicated. This is known as diffraction limit or the Abbe diffraction. So you have a limitation for this. This is given by lambda divided by 2 into numerical aperture. Numerical aperture is represented by mu into sin theta, and theta is the half angle of this cone. Now the next part, for the telescope, the resolving power of a telescope refers to the ability to distinguish between two close stars or the distinct objects. Telescope normally used to see the far object or the distant objects. Now how to resolve? So you need to follow this mathematical relation. Here the sin theta minimum, this is equal to 1.22 lambda divided by 2. What is theta? Theta is the angle between these two rays. So one is focusing one object, another is focusing another object. So the angle between these two is represented by theta. This is given by 1.22 lambda divided by D. So lambda is the wavelength obviously, and D is the diameter of the lens or the mirror of the telescope. And what are the resolution criteria? So obviously the larger D gives you better resolution. Now is used in astronomy to distinguish between binary stars or the finer planetary details. So far objects need to be distinguished properly. Now the criteria, when two distinct objects, mainly the stars, are resolved when the angular separation between them is minimum. So this angular separation must be minimum to give you the better resolution for the telescope. And the third one, this is known as diffraction grating. So what is diffraction grating? There will be number of slits, there will be large number of slits are placed, When light passes through this, the slit values, the slit width is very small, it's comparable to wavelength of light. So there will be secondary light sources, they will superpose and will produce diffraction pattern on the screen. Now if you use white light, it will pass through this and it will produce some part of the spectrum. At the central region, one can get a white bright light, but as we move with the higher order of diffraction pattern, you will get some part of the spectrum. For the optical light, the wavelength values are very close to each other. So to distinguish between two closely placed wavelengths, we need to use the concept of resolving power in case of diffraction grating. So the definition says the resolving power of diffraction grating is to ability to distinguish between two closely placed wavelengths. These wavelengths are very close, we need to distinguish between. And the mathematical relation or the numerical relation you must follow is lambda divided by d lambda. So one wavelength can be considered as lambda, but the next one can be considered as lambda plus d lambda. These values are very close. This d lambda is very, very small. So now to distinguish this, so the lambda divided by d lambda must be equal to n into small n, where n is the number of slits. How many number of slits are there in the diffraction grating? And n is the order of the fringe. So if this condition is satisfied, one will be able to resolve this condition. What are the criteria? Higher order of n and more number of slits will give you the better resolution. Use spectroscopy for different spectral lines, separate spectral lines. And the most important thing, the spectral line are just resolved when the principal maxima of one coincide with the fast minima of the other. So one can just think about that you have a central maxima, a primary maxima or a central maxima. Now, if you have your minima somewhere here, okay, after central maxima there will be minima. So when you have the minima, obviously the maxima will be prominent over there. So this must be the condition for the resolution for the diffraction grating. Thank you.